everyone. In this video we're going to talk about planes in space. In the previous video we talked about the lines in space, so we're just continuing on and expanding this idea to planes. And so if you're thinking about a plane, it's basically like, you can picture it like a sheet of paper like this. We're not going to pretend it doesn't fold though, so like this solid paper. For an equation of a plane in space, we need two things. We need to know a point in the plane and also a vector normal or perpendicular to the plane. So here's my drawing. The point in the plane would be something like P naught, and then perpendicular would be this vector n. And so the idea is, if you think about it, why we need those two things, imagine, if you can, the point, I knew the point in space, so all of space, the point on my plane was maybe right here, right in front of me. So if I knew that my plane needed to go through this point right here, well, it can kind of just do anything, this plane, right? It can rotate anywhere as long as it has this point right in front of me on it. So then if I know a vector that's perpendicular to this plane, so I know that my plane needs to go through this point in space, but also be perpendicular to this vector, then I know exactly where that plane is at. So I'm going to say straight up is perpendicular. So I have this point in space, my plane has to be perpendicular to, it's folding because it's paper, but it has to be perpendicular to straight up, which would be like this. Okay, so I'm going to use two hands. Alright, there we go. So then that would be my plane in space. So that's the idea of why you need those two things. So now let's go through the equations for it. And so two forms, one is a little bit more meaningful than the other, but basically we have the following. So this is our background for it. Let me go ahead and just say down here the plane, and this is going to be through this point I'm calling P naught. So through P naught, which has coordinates x naught, y naught, z naught, and then so that's one of the two things you needed. And then normal or perpendicular to, so normal to n, which we're going to say n is the vector with components a, b, c. Okay. Now you can put this in component form with the angled brackets, or I'm just using the ijk standard unit vector form. Either way is fine. So the plane through this point, normal to this vector, which is exactly my drawing there, can be written these two different ways. So let's go ahead and get rid of this. And so this, we'll just say, becomes the following. So we'll call it the vector equation. And I'll just abbreviate. So our vector equation just looks like this. N dot P naught P. Okay? And it's an equation, so it's got to equal something. And it actually just equals 0. Okay? So n being our normal vector here, P naught P being the vector from P naught to P. And so why does it equal 0? Well, remember when we learned about dot product, we knew that u dot v was 0 anytime that u and v were actually perpendicular, when the angle between them was 90 degrees. So this will always happen anytime you're dotting two perpendicular vectors. Now, I'm going to give you the next form of the equation for a plane. It's going to be the component form, and I'm going to go one step to get us there. So instead of just giving it to you straight, I'm going to kind of guide us to it. So the component form is going to come from kind of expanding out this dot product. So the second version, if you say n is this vector here, and I'm going to go ahead and put it in ijk form like I had down there. So ai plus bj plus ck. And I'm dotting that with the vector between these points, p naught and p. And so remember how that goes when you have a vector between 2 points. You subtract from the ending point to the starting point. So we save the subscripts of 0 for the starting point. So this is going to look like x minus x naught for I. And that would be the I component or x component for this vector, plus y minus y naught. Let's get rid of this picture now. And that's for our j component. And then last, plus z minus z naught for the k component. And that's just the vector from p naught to p. That's how we would write that out. And then if you expand this using your dot product, remember dot product, you take the x component times this x component, this y component times this y component, and so on, and you add. And so we can say now that the component equation of a plane looks like the following. We have a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and this still equals 0, okay? Because there's technically still an equals 0 there. All right. Remember, when you do dot product, it's always a number, okay? So notice I don't have I, j, and k anywhere here because these are values. So when I dotted this times this, we didn't count the I, we just said a times this quantity. So that's from the dot product. You can write this a little tiny bit different if you distribute. So if you said a times x and then a times negative x naught, you can write it like this. ax plus by plus cz equals d, where d is basically all of these ABCs times the initial values, x naught, y naught, z naught. So where d is going to be equal to a x naught plus b y naught plus c z naught. Okay, so you can write it either way. These are just your equations for a plane in space. Knowing two things: the initial point or a point on the plane, you got to know that point in space, and a vector that's perpendicular to that plane. If you know those two things, really straightforward plugging in. So let's try it. Let's find an equation of a plane given some information. Okay, so we have to find the equation. It's going to be for the plane through, okay, -3, 0, 7, and perpendicular to, let's go with 5i plus 2j minus k. Okay, so we actually have everything we need to just kind of plug right in and get here pretty quickly on this example. This is our initial point, so I'll write it out just so it's very clear. X naught is -3, y naught is 0, z naught is 7. We also know the normal vector is right here. So you can say n or ABC. You can jump right in. I'll go ahead and say both. N equals this vector here, 5i plus 2j minus k. And then you can break that down and say that A is 5, B is 2, and C is -1. And then we plug right into our equation. I'm going to go ahead and use this one here. You feel free to use the second version, but I'm going to go right into our equation for our plane, which is this. Let's just put that there. And so we have A, which is 5, times x minus x naught, so x minus -3, plus b, which is 2, times y minus y naught, which is 0, plus c, which is -1, times z minus z naught, which is 7, equal to 0. Now technically I can leave it like this, but it's not a very good format to leave it in. We should simplify at least somewhat. And so we have 5x, I'm going to distribute here, plus 15, then 2y, then over here in the back we have minus z plus 7. I'm just distributing. And then what we tend to do, like I had the other equation where it equaled d, is to take all these numbers and kind of put them on the other side of the equal sign for a final answer. And so we have 5x plus 2y minus z, and we're going to subtract 15 and 7 from both sides. And so we get negative 22. And this would be what I would call the final answer for the equation of our plane. Okay, so let me give you a note and some facts, and then we'll try another example out. Alright, so some information for you here. Let's start with this note. If no normal vector is given, so let's say you're asked to find the equation of a plane, but you don't have a normal vector, which you need to find that equation, you can use the blank of two vectors in the plane to find a normal vector. Think about it for a second. If I know two vectors in the plane and I need a normal vector, I need a vector that's perpendicular to those two vectors. I have two vectors in a plane, I need something perpendicular to them. Hopefully you remember, maybe not, I'll tell you, cross product. So the cross product, whenever you calculate this between two vectors, it's always telling you a vector perpendicular to both of them using the right hand rule. So if both my vectors are in my plane, I use my right hand rule. My cross product tells me a vector popping out of the plane or normal to it. So fact, two planes are blank if their normal vectors are blank. Okay, and this is going to be parallel. So two vectors are parallel if their normal vectors are parallel. And so if their normal vectors are both pointing, like let's say in the same direction, well then the planes must also be parallel to one another. And so we can kind of expand this right here and say that we'll call it n1. We'll just say that's our first normal vector. Remember when we talked about parallel vectors a while back? That means that one is a multiple of the other. So you could say n1 is c times n2. Just scalar multiples of each other. And that's just for some scalar c. Okay, so two vectors are parallel if they're scalar multiples of each other. And when two planes are parallel, it's because their normal vectors are parallel. Last fact here, two planes that are not parallel, think about it, think about what you knew about lines. If two lines aren't parallel, well, eventually they meet. Same thing here, two planes that aren't parallel, eventually they intersect. Okay, intersect. And what does that look like? When two planes intersect, like two sheets of paper meet, they actually meet to form a line. So two planes intersect they form a line, and that line is actually perpendicular to the normal vectors of both planes. Okay, so let's try out another example here, and it's going to have to do with parallel vectors. So looking at this example, we want to find a vector parallel to the line of intersection of these two planes. So we just talked about it. Two planes meet and they form a line when they meet. So it's a line that connects those two planes. And so we want a vector that's parallel to that line of intersection. So we kind of have to think about what we just talked about with our fact. And our fact was that that line that you get when the two planes meet is actually perpendicular to their normal vectors. So think about how you can use the math that you know to do something about that to answer this question. So here's what I'm going to first point out. Let's go ahead and call this plane 1. And so I'll call this n1. n1 is the normal vector for plane 1. Okay? And so if you remember the equation of a plane, these coefficients on x, y, and z were actually the components of the normal vector. So n1 is 3i minus 6j minus 2k. And we can go ahead and just kind of make that a little bit more clear. This is the vector normal to, we're calling it plane 1. Okay. Then for the second plane, same idea. These components as coefficients on x, y, and z make up the normal vector to that plane. So the normal vector for plane 2 is 2i plus 1j, or just j, minus 2k. And this is the vector normal or perpendicular to plane 2. Okay, so now think about it. Okay, you're kind of having to reason your way to this result here. I now know two vectors that are representing the normal vectors to the planes that they're in, and I am asked about a vector parallel to the line of intersection of these two. Well, based on that fact that we just talked about, the line is perpendicular to both of these. So what do we know about that? What can we use? Cross product. So what we need to do is we actually need to take the cross product of these two vectors, because that will result in a perpendicular vector to these two. Okay, so just a really quick visual for you. If this is n1 and this is n2, then their cross product, when I do my cross product, the vector using my right hand rule would be perpendicular to those two. There'd be like a right angle here and here. That would be n1 cross n2. And we just wrote down that the line of intersection is perpendicular to both of those. So our line of intersection might be like somewhere over here, but it's going to be parallel to this cross product. Okay, so I know it's a little weird getting there, but the idea is we just wrote down a fact about the line of intersection being perpendicular to these normal vectors. So if we take these two normal vectors, cross them, we're going to get this perpendicular vector, which we need because it's parallel to our line. All right, so we've done this previously, but I'll just kind of quickly go through the calculation with you. Crossing these two vectors for our 3x3 matrix, row 1 is ijk, row 2 is n1, which is 3, negative 6, negative 2. Row 3 is n2, 2, 1, negative 2. And then you're going to just compute your determinant of your 3x3 matrix here. And hopefully you're feeling okay about how to do that. I'll just sort of break down the steps for you real quick and then give you the answer. So the 2x2 with I is going to be negative 6, negative 2, 1, negative 2, minus the 2x2 determinant for j, which is going to be 3, negative 2, 2, negative 2, plus the 2x2 determinant for k, which is 3, negative 6, 2, 1. And if you work that out, I ended up getting that this equals 14i plus 2j plus 15k. And we were asked to find a vector parallel to the line of intersection, and we did that by calculating this cross product. Okay, so now if you want, you can actually verify using some kind of graphing utility like a 3D grapher. There's lots of nice websites that do this. I tend to use like GeoGebra 3D if you want to kind of verify visually that this is in fact parallel to this line of intersection for the planes. So the last two things I'm going to mention to you guys is the distance from a point to a plane, and then also something to do with the angle between planes. So here's this distance formula. The distance from a point S to a plane, and with that plane we know a normal vector and a point P. Okay, so the question is about how far is this point to this plane, and you always pick the shortest perpendicular distance. And so technically you're kind of like this. This is what we're looking for. Now the way that we solve for this mathematically is actually to go over to this normal vector wherever P happens to be at. So yes, this is going to be our distance D, but we're sort of going to form a triangle over here with this normal vector N, this vector normal to our plane. And so let me kind of go across here, and then P to Q as well, and we actually have this triangle that we can form. And so this distance that we're looking for is really this side of this triangle, which is kind of interesting. And so what we end up getting here for this calculation is the following formula. So we have that the distance, d, is equal to the magnitude of the vector ps dotted with the unit normal vector here, n. So we have n over its magnitude. And so what we're interested in here is actually just the direction of n. That's what this is giving us when we turn it into a unit vector. And then ps is this vector from point P to our point S. And so what this really is, if you remember a couple of videos back, this is actually the projection of ps onto n. So just so you're aware of, or the length of it technically because of this magnitude. So this is really just the length of the projection vector of ps onto n. And we even kind of broke that down before. The length was actually called the scalar component of the projection of ps onto n. So just a little bit of more meaning to it. So officially, like to remind you what that was about, if you kind of take a light and you can shine it perpendicular to this vector ps, the shadow it would cast would be this projection vector right here, which is the distance. So this is how you would calculate it. So I just wanted to give you that formula. So I'm going to tell you one more thing, and it happens to be regarding the angle between between planes, and then we'll work out an example with that, and that'll be it for this section. Alright, so here's this last piece of information. The angle between two intersecting planes is the acute angle between their normal vectors. Why this is interesting is because we've actually already calculated angles between vectors before. So if we can kind of break this down, even though we're talking about two planes intersecting, we can just break it down into two vectors and the angle between them. So let me show you what I mean with this last example here. If you recall, the angle between two vectors was cosine inverse of, we had the dot product of the two vectors in the numerator, and we divided by the magnitude of those vectors in the denominator. So if we have two planes that intersect, then as long as we know the normal vectors from those two planes, we can use them in this calculation, and then we'll actually know the angle between those two planes where they intersect. And so for this example here, let's just say that plane 1, two planes intersect, and plane 1 is 3x minus 6y minus 2z equals 15. I think that was from our last example. And then plane 2 is 2x minus, let's say plus y minus 2z equals 5. And so we'll just quickly calculate the angle between them when they intersect. So let's identify the normal vectors, and then we'll plug them into our calculation for our angle between the planes. And so from this equation of a plane, it's really straightforward. We just have that the normal vector here would be 3, negative 6, negative 2. The normal vector for the second one, normal vector here would be 2, 1, negative 2. And then let's go right into our equation for our angle. So theta is cosine inverse of, and we can kind of do this all at once here. The dot product is on top, so dot these two vectors. So remember how that goes. Multiply component-wise and then add those together. So 3 times 2 plus negative 6 times 1 plus negative 2 times negative 2. So that's 4. And then on bottom, I do need to calculate the magnitudes. So let me just do that off to the side here. So the magnitude of n1 is going to be the square root of 3 squared plus negative 6 squared plus negative 2 squared. And that looks like 9 plus 36 plus 4. So that's square root 49. So we're going to get 7 for the magnitude of our first vector. And then times the magnitude of the second one here. So that's going to be square root of 2 squared plus 1 squared plus negative 2 squared. That's 4 plus 1 plus 4, square root 9. So that's 3. Okay, let's make this look a little better. On top we're going to get 4. So cosine inverse of 4 on bottom, 21. So that will be the exact answer. That's our angle between our two vectors, or sorry, technically between our vectors, but between our two planes where they intersect. Let me just give it to you in a little bit more meaningful ways. If you're in degrees, this is about 79 degrees, and if you are in radians, this is about 1.38 radians. All right, so that's it for planes. See you in the next one.